Welcome to the deep dive. Today, we're digging into something that's really shaking up how we handle data.
Yeah, it's a big
If
one.
you work with data, you've definitely seen it.
Yeah.
Just the explosion, right? The sheer amount of data, how fast it's coming at us, and all the different types, especially from things like IoT
Oh,
devices.
absolutely. That velocity and variety, it's intense.
And trying to keep up using the old ways, it feels like trying to drink from a fire hose with a tiny straw.
Right. They just weren't built for it. Traditional methods, they struggle, especially when you need those insights, like now.
They really do struggle. Those sort of old school pipelines, batch processing, manual ETL stuff, they feel pretty fragile, honestly, and slow.
Definitely slow. Not suited for this real-time world we're in now.
Exactly. So that's what this deep dive is all about. We're looking at how artificial intelligence, AI, is, well, basically transforming data engineering. And we're going to focus particularly on two kind of heavy hitters that are essential for building these scalable real-time pipelines: Apache Flink and Apache Kafka.
Yeah, these two come up again and again, and we've got some really good material to draw on today.
What about?
Well, we've looked at articles covering the big AI trends in data engineering. Also, the huge news about the Apache Flink 2.0 release.
Oh, yeah, the first major one in ages, right?
9 years, so that's significant. We'll get into what Flink does well, some of the, practical challenges too. And there's this fantastic piece about running Kafka and Flink at massive scale, like Salesforce scale.
Wow, okay. Real world stuff.
Exactly, in the trenches. Plus, we've got insights into newer concepts like edge AI and just the core principles of building these real-time systems properly.
Okay, so the plan is unpack the problems with the old ways, see how AI, Flink, and Kafka are changing the game, look at some cool examples, get into the nuts and bolts of Flink 2.0, and importantly, talk about the real-world challenges and things you need to consider.
Sounds like a plan. So where should we start? Maybe digging a bit deeper into why traditional data engineering is struggling so much right now.
Yeah, let's do that. Because it wasn't always this hard, right?
Mm-hmm.
But the landscape shifted. Fundamentally, a lot of traditional data engineering involved engineers, like manually writing code.
Uh-huh. Scripting ETL jobs, debugging them, maintaining them.
Exactly, very labor intensive. And, humans make mistakes, so error prone, and just not built for the speed and scale we see now.
And that manual approach, it causes a whole bunch of other problems downstream, doesn't it?
Absolutely. First off, just the operational overhead. It's huge. Engineers spend so much time on these repetitive tasks, coding, fixing, tweaking.
Time they could be spending on, say, better architecture design or, actual innovation.
Right. Then there's the data complexity problem. Where's the data coming from now? Everywhere.
Yeah, it's not just nice, clean databases anymore. You've got IoT sensor streams, APIs spitting out data, application logs, unstructured stuff like images, text.
Stuff traditional tools just choke on, basically. They weren't designed for that messiness.
And trying to ensure data quality and governance with all that chaos flowing in, it's incredibly difficult.
Yeah, how do you make sure it's accurate, consistent, compliant with rules like GDPR? At scale, it's a massive challenge. Get it wrong, and you're making bad decisions, potentially costs us a lot of money.
And then scalability. Those static pipelines, they just hit a wall.
They really do. They become bottlenecks as soon as data volumes grow, causing delays, backlogs. It just doesn't work.
Which often means higher costs, right? Trying to manage cost management is tough. You either over-provision resources in the cloud just in case,
And pay for stuff you're not using.
or you under-provision and things fall over. It's inefficient.
But finding the people to manage all this, that skills gap is real. Good data engineers who can handle modern, complex systems are hard to find and expensive.
Definitely. So that paints a picture of the challenges. It's a tough spot.
It is. But this is where it gets really interesting, because AI isn't just for the analysts anymore. It's actually changing the engineering itself.
That's the key insight, I think. AI is tackling these exact pain points. It's automating the tedious stuff and adding intelligence right into the pipeline process.
Okay, so how specifically is AI helping? What do the sources say?
Well, one really surprising thing is just how much AI is focused on automating the grunt work. It's about freeing up those engineers.
Like what kind of grunt work?
Think about building ETL pipelines. Tools like AWS Glue or Informatica's Claire platform, they actually use AI to suggest or even auto-generate pipeline code.
Really? So less manual coding.
Exactly. AI can also look at historical pipeline runs and predict potential failures, sort of like predictive maintenance for your data flows. And you see these low-code or no-code platforms like dbt or Dataiku often using AI under the hood to make development way simpler.
Okay, that tackles the overhead. What about that data complexity issue, all the messy sources?
AI helps there too. It can do things like schema inference, figuring out the structure of data even if it's unstructured. It enhances platforms like Kafka and Flink to better handle those fast, complex, real-time streams. And things like natural language processing, NLP, are crucial for pulling insights out of raw text data.
Makes sense. And data quality, keeping things clean and trustworthy.
AI is a huge help for data quality and governance. There are specialized tools now, like Monte Carlo or Great Expectations, that use AI to automatically spot anomalies.
What kind of anomalies?
Things like, sudden weird values, schema changes you didn't expect, data drifting over time. AI can also help generate the actual data quality tests you need to run, and it's being used more and more for data lineage tracking, figuring out where data came from, how it changed. Super important for compliance.
That automated monitoring sounds like a game changer. No more manual spot checks?
Pretty much, or at least much less reliance on them. And then scalability AI is key here too.
How so?
Platforms like Databricks or Google Dataflow use AI to automatically adjust the compute resources based on the actual workload. So it scales up when busy, scales down when quiet, no more guessing or manual scaling.
That must help with costs.
Definitely. AI helps optimize things like how data is partitioned or indexed, and it's fundamental to how distributed frameworks like Apache Spark work efficiently, which directly impacts cost management. AI analyzes usage patterns to schedule jobs more efficiently, adjusts resources dynamically to avoid paying for idle machines, and can even help predict future cloud spending.
Okay, so it's making things more efficient, more scalable, cheaper. What about finding the people? That skills gap.
AI helps bridge the skills gap, too. Firstly, automation just reduces the amount of manual coding needed. Secondly, these AI-powered platforms are often more intuitive, making powerful tools accessible to people who aren't deep infrastructure experts, like data analysts.
So democratizing data engineering a bit.
Kind of, yeah. And many platforms now include AI-driven tutorials or guidance right within the tool, helping people upskill as they go.
So it really feels like AI is more than just a feature. It's like fundamentally changing how data engineering gets done.
It really is. It's a paradigm shift. Faster insights, lower costs, more reliable pipelines, and it frees up engineers to innovate, which is huge.
Making the whole process smarter. Okay, so AI provides the intelligence, but for the real-time part, you need a powerful engine, right?
You absolutely do. And that's where Apache Flink really shines. It's become a real leader in stream processing.
What's its core strengths?
Handling continuous data streams with really low latency and super high throughput. It's built to handle that fire hose of data we talked about as it arrives.
So even before this big 2.0 update, what made Flink so good for streaming?
Several things. It offers true stream processing. It wasn't an afterthought. It was designed ground up for continuous event-by-event processing. This gives it low latency and high throughput, which is essential for things like fraud detection or real-time recommendations.
Okay, speed is key.
Definitely. But also stateful stream processing. This is massive. Flink lets your application remember things across events, maintain state, like tracking user behavior over time or calculating running totals.
So it has memory, context.
Exactly, which you need for anything complex, especially ML pipelines running on streams. It also handles data arriving out of order correctly using event-time processing, guarantees exactly one's consistency, so no missed or duplicated data critical for data integrity.
Reliable, then.
Very. And it's built for scalability and fault tolerance. It can scale out to thousands of machines, and it uses clever checkpointing and recovery mechanisms so jobs keep running even if nodes fail. Plus, it always had this goal of stream batch unification, trying to let you use one system for both kinds of processes.
That's a solid foundation, but it hasn't stood still. This Flink 2.0 release sounds like a big deal.
Oh, it's huge. Apache Flink 2.0 released March 24, 2025. Like you said, first major version bump in 9 years. That's 2 years of work, 165 contributors. It's a massive overhaul.
9 years. Why now? What was driving such a big change after so long?
It was a mix of things. They needed to tackle some existing challenges, like Flink could be costly to run resource-hungry and had a reputation for being complex, that steep learning curve.
Uh-huh.
But also, the world changed. Cloud-native architectures became dominant, data lakes evolved, and then AI and large language models exploded onto the scene, creating new demands. Flink needed to adapt.
Okay, so what are the headline features in 2.0? What's the really new stuff?
The absolute biggest architectural shift is disaggregated state management, sometimes called FORCE.
Disaggregated state. What does that mean?
It means separating the storage of your application's memory, its state, from the computer's actually doing the processing.
Okay. Why is that important?
It's crucial for the cloud, especially environments like Kubernetes where your compute instances might appear and disappear.
Mm-hmm.
If state is tied to compute, scaling or recovering is slow because you have to move all that state around. Decoupling makes scaling much, much faster.
Got it. Any performance benefits?
Yes. Benchmarks like Nextmark showed it's still really fast, even with limited local cache for state. And even with no local cache, it could still achieve about half its peak performance because of a new asynchronous way it accesses state. This also makes checkpointing saving the state lighter and quicker.
So faster scaling, better performance in the cloud. Makes sense. What about that stream batch unification goal? Any progress there?
Big progress. Stream batch unification improvements. They've really enhanced materialized tables.
Materialized tables.
Yeah, think of them as tables that are automatically kept up to date by a streaming query. They simplify architectures where you need both real-time updates and access to historical data from one place. They're much more production-ready now, better handling for schema changes, easier deployment on Kubernetes or Yarn, and tighter integration with Apache Paymon for data lake scenarios.
That sounds incredibly useful, combining real-time and history easily.
It really is. And for the batch side, there's adaptive batch execution. Flink can now optimize batch jobs based on what it sees at runtime.
How does that work?
It has new tricks like adaptive broadcast join. It decides during the job if one side of a join is small enough to just send to all nodes. And automatic join skew optimization helps deal with uneven data, which often causes slowdowns. Benchmarks like TPCDS showed like an 8 to 16% speed up compared to the previous version.
Nice. Free performance boost. And you mentioned data lakes.
Yeah, deeper streaming lakehouse integration, especially with Apache Paymon. Things like pushing filter logic down into the lake storage, better performance for joining stream data with lake data. You can even manage the Paymon tables using Flink SQL now.
Okay, connecting streams and lakes more tightly.
Oh.
What about the connection to AI? We started there.
This is super exciting. AI integration. A related project, Flink CDC, Change Data Capture, recently added the ability to call out to AI models directly in your data transformation logic.
Whoa, really? Like inside the Flink job?
Yeah, so imagine capturing a database change and right then, in the stream, calling an OpenAI model to, say, do sentiment analysis on some text, or sort items, or detect an anomaly. Flink 2.0 itself adds new SQL syntax to make defining and calling AI models feel just like calling a regular function.
That opens up possibilities, like doing retrieval augmented generation, RAG, directly on streaming data.
Exactly. Combining real-time stream processing with sophisticated AI inference within the same pipeline. It's powerful.
Very cool. Anything else notable under the hood in 2.0?
There's an experimental new DataStream v2 API aiming for simplification. The SQL gateway is easier to deploy, support for newer Java versions like Java 21, and removal of old Java 8 support. Plus improved serializers for better performance.
Okay, that's a ton of changes. If someone's running, say, Flink 1.18, what's the upgrade path like? Is it easy?
Not exactly easy. It's important to know there are significant breaking changes. This isn't just a minor update.
Like what?
The old dataset API for batch is gone. Older source and sync APIs are removed. The main config file name changed. And crucially, the way Flink stores its state isn't generally compatible between 1.x and 2.x. You'll likely need to use Flink's SavePoint feature to take a snapshot before upgrading. It's a major evolution, requires planning.
Good to know. It's a big step. Okay, so Flink is this real-time processing beast, especially now. Where does Kafka fit into this picture? Why do we always hear Flink and Kafka?
Because there's such a natural pairing, Kafka acts as the super reliable, scalable message broker. Think of it as the central nervous system for your data streams, or maybe a shock absorber.
A buffer.
Exactly, a durable buffer. Data producers write to Kafka topics, and then Flink jobs read from those topics reliably, process the data, and maybe write results back to Kafka or somewhere else.
That Salesforce distributed tracing example you mentioned earlier, they use both, right?
Perfectly illustrates it. They had huge amounts of tracing data initially landing in S3 files. They built a custom Flink source connector to read that Avro data from S3.
Okay, data comes into Flink.
Then the Flink pipeline did the work, filtering out noise, sampling data, adding keys like the trace ID so related events stick together, and using sliding windows to aggregate metrics over time, grouped by service name.
And after Flink processed it.
It used a Kafka sync to write the cleaned aggregated data to a Kafka topic. Kafka then acted as that reliable buffer again before downstream consumers picked it up to load into Elasticsearch or Druid for analysis.
And the scale was serious.
Oh yeah, multi-terabytes per day, hundreds of users. Proper enterprise scale.
What were the main wins they got from that Flink Kafka setup?
They got much lower latency access to the processed data. It was easier to enrich the data with metadata while it was in flight in Flink.
Yeah.
Those aggregations Flink did, they massively simplified the queries they needed to run on the back-end systems. And just doing things like sampling or filtering became much simpler within Flink itself.
So Flink handles the complex processing, Kafka handles the reliable transport and buffering. Makes sense. Beyond that tracing example, what other kinds of real-world things are powered by this duo?
Oh, loads of stuff. Real-time analytics is a massive area. Think instant fraud detection, analyzing transactions the moment they happen.
Right. Critical for finance and e-commerce.
Definitely. Or personalized recommendations that update immediately based on what you're clicking on a website or watching on a streaming service. Or monitoring thousands of IoT sensors in real time, maybe for food delivery tracking, or managing smart home devices.
Acting immediately on incoming data.
Precisely. They're also fundamental for event-driven architectures, systems that need to react instantly to things happening. Flink's statefulness is key here again for maintaining context in dynamic systems like fraud or recommendations. And they're increasingly vital for machine learning pipelines.
Also,
Continuously processing data streams to feed models for training or, more often, for real-time inference. Flink integrates with ML frameworks and lets you deploy models that make predictions on live data with minimal delay.
let's double-click on fraud detection for a second. How does Flink specifically help there?
Well, it analyzes those transaction streams in real time, but the key is the stateful computation. Flink can track, say, a user's transaction velocity over the last hour, or maintain their current account balance, or compare against historical spending patterns, all updated instantly with each new transaction. Kafka ensures none of those transactions get lost. And Flink's complex event processing, CEP features, let you define patterns, like specific sequences of events that might signal fraud.
Okay, that stateful tracking is crucial. What about IoT, handling all those devices?
IoT data processing is another sweet spot. Flink's designed for that sheer volume and speed. It can run complex analytics directly on the streams, looking for patterns, triggering alerts. Its low latency is vital for things like predictive maintenance, spotting issues before machine fails, or optimizing energy grids. It handles diverse IoT data formats, and its fault tolerance is essential when you're dealing with critical applications, maybe in healthcare monitoring.
Taking that fire hose of device data and making sense of it immediately. Now, speaking of devices, what about processing even closer to the source? This idea of edge AI.
Yeah, Edge AI is getting a lot of attention. It's basically about running AI algorithms and models directly on the local edge device itself.
Like on the sensor
Yeah,
or the camera.
could be. Or on a gateway device, or maybe a more powerful computer in a vehicle or factory floor. The point is, you process the data there locally instead of sending everything back to the cloud first.
What's the advantage of doing that?
Several big ones. First, latency. It's much lower because you don't have that round trip to the cloud, which means faster reactions. Second, bandwidth. You're not sending massive amounts of raw data over the network, which saves costs. Third, you get true real-time analytics right on the device. Fourth, data privacy can be improved because sensitive data might stay local. And it offers a different kind of scalability, often using a hybrid cloudage model, plus potentially lower costs overall, less cloud compute, less network traffic.
Okay, low latency, less data transfer. I can see the appeal. How does Flink fit into this edge picture?
Flink's core strengths, processing continuously with low latency, managing state reliably, make it actually a really good fit for running on these sometimes resource-constrained edge devices.
So you could see Flink powering intelligence in. What kind of devices?
The sources threw out some potential future examples, maybe things like the Tesla Optimus robots needing real-time analysis, or even devices like the Apple Vision Pro using Flink for low-latency edge processing.
Oh,
Purely speculative, but illustrates the potential.
interesting. But there's a concrete example too, right? That logistics case study?
Yes, that one was really compelling. A logistics company actually deployed Apache Flink onto edge devices in their delivery trucks.
With Flink running in the truck.
Exactly. It processed GPS data, engine sensor data, maybe driver behavior metrics right there at the edge. It could detect route deviations, potential maintenance issues, things like that, instantly.
And enable immediate action.
That was the key. Immediate insights allowing for immediate corrective actions, maybe rewriting the truck automatically or alerting maintenance. Then the aggregated insights, the summaries, the important alerts were sent via Kafka back to a central dashboard for monitoring.
So local processing for instant action, central aggregation via Kafka. What was the result?
They reported a 40% reduction in delivery latency.
Wow, 40%. That is significant. That really shows the power of pushing processing to the edge with Flink, coupled with Kafka for the central view.
It's a powerful hybrid model. It feels like a glimpse into the future of real-time data engineering, especially for these kinds of operational systems.
Okay, so running these systems, whether it's Salesforce handling terabytes or Flink running in a truck, clearly requires mastering scale and performance. What practical lessons did the sources share? What did the Salesforce team learn?
They shared some really valuable, hard-won insights. For Kafka optimization, tuning producer settings is critical. Things like batch.size and linger.ems, basically how much data to group together and how long to wait before sending. Getting that balance right affects throughput and memory. Compression matters too. They found gzip saved a lot on AWS data transfer costs, but LZ4 offered a better balance with lower CPU use. And how you partition your Kafka topics is vital to avoid one partition getting overloaded. They even built a custom partitioner and used newer Kafka features to handle data skew better.
Makes sense. What about tuning Flink itself for performance?
Flink optimization starts with resources. CPU-wise, maybe 1 to 2 cores per processing slot is often okay, but memory is crucial, especially for stateful jobs that need plenty.
Yeah.
Using an efficient garbage collector like G1GC helps. And constantly monitoring for back pressure using the Flink UI or metrics is key. It tells you where your bottlenecks are.
Back pressure meaning one part of the pipeline can't keep up.
Yeah, exactly. If you see it, you might need to increase parallelism for stateless steps, but that costs more resources. Optimizing network buffers, memory.fraction, buffer.timeout settings in Flink helps absorb bursts of data.
What about tasks that need to talk to external systems, like a database, that could slow things down?
Big time. They heavily recommended using Flink's async functions pattern. This stops a task from blocking the entire processing pipeline while it waits for that external call to return. It makes a huge difference. Also, avoid super long-running calculations within keyed operations. Use time-bound windows instead, and always analyze your key distribution. If data for one key swamps a task, you need custom partitioning.
And managing that crucial Flink state.
Use a robust state backend, like RocksDB, especially if you have large amounts of state, and make friends with Flink save points. These are snapshots of your job's state that you trigger. They're essential for safely restarting, upgrading, or rescaling your jobs without losing data.
Okay, what about getting data into and out of Flink reliably and fast? Sources and sinks.
First, avoid slow serialization formats like JSON if you need high throughput. Use efficient binary formats with schema enforcement, like Avro or Protobuf. Avro is often favored for its schema evolution support via schema registries.
And writing to Kafka reliably. No duplicates, no messages.
For the Kafka sync, use the properties that enable exactly once semantics. That usually means setting enable.idempotence to true on the Kafka producer side and using transactional.aid in Flink's sync. This uses Kafka's transaction capabilities, a two-phase commit, to guarantee messages are written exactly once. Also, think about source retries or sending problematic messages to a dead letter queue for later inspection. And definitely use SSDs for storing Flink's persistent state recovery after a failure is way faster.
And infrastructure-wise, any big lessons?
Huge one. Network matters. They saw a 6-fold latency improvement just by running their Flink clusters in the same cloud account, same region as their Kafka clusters. Keep them close.
Good tip. And what about scaling Flink jobs up and down automatically?
There are options. You can use tools like Yarn on Demand or Flink's built-in reactive mode since version 1.2, which tries to use available resources. Or if you're on Kubernetes, you can use the horizontal pod autoscaler, HPA, with custom metrics like job throughput or latency to drive scaling decisions.
That's a wealth of practical advice. It really highlights that Flink and Kafka are powerful, but they're not exactly set-it-and-forget-it technologies at scale.
Not at all. They require expertise. Which brings us to the other side of the coin, the drawbacks and challenges of using Flink.
Right. It's not all sunshine and roses. What are the main hurdles?
The most common complaint you hear is the steep learning curve. Flink is powerful because it's complex. Understanding state management, event time semantics, the different APIs, it takes time and effort to get your head around it all.
And finding help isn't always easy.
That's another point. Sometimes limited documentation and community support. Compared to something like Spark, which has been around longer and has a maybe broader user base, finding answers to specific, tricky Flink problems online can be harder. The docs might have gaps, especially for advanced operational stuff.
Which makes troubleshooting more difficult.
It can, yeah. And it adds to the overall complexity in setup and maintenance. Running Flink reliably at scale isn't trivial. It needs careful planning and skilled operators. Plus, as we touched on, it often has high resource requirements. That stateful, high-throughput processing needs significant CPU, memory, and often fast storage.
So it's powerful, but maybe not the right tool for every single job.
Exactly. Flink excels at complex, large-scale, low-latency, stateful stream processing. If your needs are simpler, it might genuinely be overkill. The complexity and resource cost might not be worth it.
So if Flink seems too heavy, what are some alternatives people might look at?
For simpler streaming tasks, especially if you're already using Kafka heavily, Kafka Streams is a library that might be sufficient. It's simpler, runs within your application. Materialize is interesting. It takes a database approach, letting you define real-time views with SQL. If you want a fully managed cloud service, Google Dataflow is a major competitor built on similar principles. And there are newer players like Redpanda, Kafka compatible, aims for simplicity, Rising Wave, SQL streaming database, and Decodable, a managed platform aiming to abstract complexity.
Okay, so choices exist depending on your specific needs and tolerance for complexity.
Definitely. You need to weigh Flink's power against its operational overhead.
Well, this has been quite the journey. We've looked at the pressures driving change in data engineering, how AI is stepping in to automate and enhance, the serious power of Apache Flink, especially with 2.0 with synergy with Kafka, and even pushing processing out to the edge.
Yeah, and despite those challenges we just discussed, the learning curve, the resource needs Apache Flink, particularly now with 2.0, really does cement its place as a leader, maybe the leader, in advanced stream processing. Its embrace of AI integration and its fit for edge computing scenarios suggests it's going to remain incredibly relevant.
It feels like for certain types of problems, high volume, low latency, complex stateful logic like fraud detection, massive IoT ingestion, real-time ML Flink is becoming less of a choice and more of a necessity.
I think that's fair. And for you listening, when you're thinking about these tools, it really comes down to evaluating your specific needs. How demanding is your workload? What skills do you have on the team? What's your infrastructure like? You need to decide if the power and scalability Flink offers justifies tackling its complexity and resource demands.
Absolutely, it's a trade-off. But thinking about that future, as data just keeps growing, keeps getting generated further out at the edge.
Here's a final thought to ponder. We talked about Flink on the edge, Kafka in the center, but how much further does that shift need to go? As demands for truly instantaneous, real-time insight and action increase across everything, how will processing power and intelligence need to distribute themselves even more radically, perhaps moving even further away from centralized clouds in the future?
A really interesting question to keep in mind as this whole landscape continues to evolve so rapidly. That's all the time we have for this deep dive. Thanks for joining us.